Thank you, and good morning, everyone, and welcome to this session where we're going to explore how technical problems cause organizational friction. And the basic idea in this presentation is that a lot of organizational problems that you might have seen, like access coordination and communication within a team, they actually have technical root causes. And the fascinating thing about that is that consequently, they can be mitigated via technical improvements. And this is something we're going to explore through 5 socio-technical smells that we're going to visit over the next 40 minutes. And the first socio-technical smell I want us to talk about is something I call the overcrowded system. So let's see what that is. And I'd actually like to introduce this particular smell to you by giving a book recommendation. So what you're going to see now is the best book that hasn't been written yet. So this is one of my personal favorites, Devoxx, The Art of Doing Half the Work in Twice the Time. Ever experienced that? So this actually comes from something I experienced myself many years ago. So at that time, I worked for a product company. And this company, they had spent 2 years developing a new subsystem. The project had missed deadline after deadline. And now the timing was critical because that project had to ship in just 3 months. Otherwise, the company would be subjected to quite some heavy financial fines, right? So it was really, really urgent. And in order to try to catch those deadlines that just flew by, the project had also scaled up the staff a lot. So there were now 25 people working full-time on that project. And one day, I found myself called into a management meeting. I hadn't been involved in that project myself before, but now me and a colleague had to sit down with the management, and the management simply asked us, can you take a look at this project and see what you can do to rescue it? Because we really had to ship in 3 months. You can do whatever you want, but we need to ship in 3 months. So we said, okay, fine, we're going to do that. So we went back to the drawing board, we analyzed the code, we took a look at it, we talked to the people on the project, and then we got back to management and we said, you know what? We have some good news and we have some bad news. Let's start with the good news. The good news are, we are confident that we can ship this in 3 months. And I mean, you could literally, see the relief in that room, right? Everyone looked so relaxed suddenly. But then someone asked, but you said you had some bad news too. This is excellent. I said, yeah, the bad news are, you're not going to like what we're going to do. Because what we are going to do is that we're going to take all that code that you have developed over 2 years and we're going to throw it away and we're going to start from scratch. And they looked a little bit shocked, right? But we kind of managed to explain and motivate why we needed to do that and why that was a faster way. And then they asked us, so what do you need to pull this off? How many additional people would you need? And I said, we're going to need 5 people. So it's, oh yeah, so 5 additional people. That's not so much. So we want to go from 25 to 30. I said, no. We want 5 people in total. And I have to admit, to this very day, I'm still surprised that we managed to get the go-ahead with that project. The reason we could do that with confidence was because I had read this book, The Mythical Man-Month. Has anyone ever read that one? Not so many people. The rest of you, really put this on your reading list. It's a great, great book. Today, it's best known for what we now call Brooks' Law, that adding people to a late software project makes it even later. And the fascinating thing is that in that book, Fred Brooks, the author, he even has a formula that explains why that is the case. And I've tried to plot it for you here. So the way you read this diagram is that on the x-axis, you have the number of potential people you can put on a project. And on the y-axis, you have the number of months until completion on whatever task you're working on. And you see here that to some degree, you can add more people, in this case, maybe 3-4 people, and you will get a faster completion date, right? You will ship quicker. But beyond some point, you see that each additional individual that you add is going to become a net loss, right? And the reason for this, Brooks claims, is because with each individual that we add, the coordination needs and the communication needs are going to increase almost exponentially. And at some point, each added individual, the extra hours you become available, they're simply going to be consumed by that access coordination and then some. So when you find yourself in a situation like this, there are really just 2 things you can do. The first option is of course to try to shrink the organization so that you kind of fit the modularity of the work to be done. Because remember, this is software, and software work development is not perfectly parallelizable, right? There's only a finite number of tasks that we can do in parallel successfully, right? So shrink the organization to fit that work that you need to do. The other option is to redesign and re-architect so that we can accommodate more people. We can allow more work in parallel by having a higher modularity in our software organization. And in this session, we're going to see examples on both of these. What we choose for that project I just told you about that had to be completed in just 3 months was option 1. That's why I went from 25 people to just 5 people, right? Now, maybe I should spoil the end result. Let's do a quick poll here. How many think that we actually pulled that crazy idea off and rewrote and delivered in just 3 months? So that's like maybe 1/3 of you. So it's a skeptical crowd, I see that. I mean, of course, we managed to ship it, but not in 3 months. We actually just needed 2.5 months. I mean, if it wasn't a success, I wouldn't have told you about it, right? But the reason I tell you that story is because to me, it's an indicator of the massive amount of waste that we have in the software industry due to a failure of finding this socio-technical alignment. So I've been thinking about that a lot. Why do we keep making the same mistakes? Because Brooks' Law, after all, it's from a book written in 1975, right? So we have known about this for 50 years and still we keep repeating the same mistakes. Why is that? I think I know the answer. So let's do a small test here. Please, have a look at the following code. Who can tell me if that code is a major coordination bottleneck for our 5 different feature teams? Or if all of that code is written by just one individual so that we might have a key person dependency? No one can tell me. It's impossible, of course. And the reason it's impossible is due to something I like to call the grand tragedy of software design. That the organization, we, the people that build the system, were invisible in the code itself. And consequently, it becomes so easy to fall into all these socio-technical traps. So what can we do instead? Well, there are a set of analysis techniques that I've been working on over the past 15 years. I call them behavioral code analysis. And if you haven't heard about behavioral code analysis before, the basic idea in a behavioral code analysis is that the code is important. A proper design is always important. But it's even more important to understand how we, as an organization, interact with the system we're building. So what we're going to do now is that we're going to embrace behavioral code analysis, and we're going to see how it can help us detect and act upon some of these socio-technical smells. And the next one we're going to explore is something I call coordination bottlenecks in code. So let's see what that problem is. What do you think of this architectural diagram? This is my generic architectural sketch. This is what like 9 out of 10 business applications look like today, right? So we have a bunch of different subsystems. Maybe they are services, maybe they're just modules. And they have a bunch of different databases, document databases, relational databases, and so on. And of course, we have a bunch of different clients, right? So we might have mobile clients, we might communicate with other systems, we have something like REST, and so on. Now, I like to claim that already here, already at this scale, it's virtually impossible for the human brain to grasp all the details. There's no way we can squeeze all the complexity of a system like that into our head and reason effectively about it. And guess what? We don't. What we do instead is that we use something called mental models. So when we think about a particular problem, a particular piece of code, very few of us have a literal representation of the code in our head. What we do instead is that we have a simplified mental model that we reason about, right? Now, the interesting thing with mental models is that they are very sensitive. They're very sensitive because the more developers we have working on the same code, the harder it becomes to maintain stable mental models. So why is that the case? Well, let's look at it this way. Let's say that you wrote a piece of code yourself today, and when you return to that code 3 days later, it looks completely different because 5 other people have been working on it in the meantime, right? So this means that when you come back to the code, you have to either kind of relearn it, right? Which means you're going to be in a constant onboarding mode, which is really, really expensive. Or you're going to make changes to that code based on an outdated mental model. So it's no wonder that bugs tend to cluster in this type of congested code. So if we have a serious organizational smell like that, like congested code, many developers work in the same parts of the code for unrelated reasons, how can we discover that problem and highlight it? In the behavioral code analysis we're going to do now, we obviously need some behavioral data. So we're going to embrace Git and Git logs, and you see a simple example here. So the only thing I do now is that I look at the Git log and I see which files have been modified by multiple authors within a given time period, maybe let's say last month. And I can do some simple statistics upon that. This is an example using some open source I wrote many years ago called CodeMat, still available on my GitHub. So I can point this tool to a particular Git repo. It will go to the Git log and it will simply see which files are developed by most authors, right? So where are the coordination bottlenecks? In this particular case, I see that the coordination bottleneck seems to be in the build system. So there is this Python file, right, builder, that has been modified by 13 different people over the past month, right? So it looks simple enough. However, textual data like this makes it really hard to spot overall patterns. So this is why I'm a big, big fan of visualizations. Because visualizations, they tap into one of the most powerful pattern detectors that we have in the known universe, the visual brain. So I want to walk you through this visualization so that we know what we're looking at. And by the way, this is a real code base with real data. This is Folly, which is a Facebook implementation of a modern C++ library. So the way you read this visualization is that each one of these large circles that you see there on screen, one of them is highlighted, they represent top-level folders. So if you do this on your own code base, you would recognize the names of these circles as important subsystems or high-level components, or maybe even services. We also see that inside each one of these folders, each file with source code is visualized as a colored circle. And you see that those circles, they have different size. Some are small, some are much bigger. So the size simply indicates the number of lines of code in each module, right? So the more lines of code, the larger the circle. And then you see that they have different colors. So the color simply reflects the author density, like how many people have worked on that code. The more people, the more red the circle becomes. So now that we know what we're looking at, let's zoom in on some of the interesting patterns. Because you see here that the package I highlighted, it's the async socket packages, really seems to stand out, right? There are lots of these red circles inside it. So let's zoom in on it and let's look at the numbers. So what we see here is that the number one coordination bottleneck, the large red circle there, you see that that code has been developed by 58 authors over the past year. 58 authors. So imagine working on that code, right? Even if you do a contribution today, you look back at it and there have been like 57 other people working at the same code. How easy is it to maintain a stable mental model of that code? So when I find something surprising like that, what I always do is to try to understand the root cause. And in this case, it's a technical root cause. So let's look at a little bit of code here. And I do understand that starting out on a Friday morning by looking at some C++ might not be everyone's idea of a great start. But bear with me, we don't need to look at the details, we just need to look at the overall patterns. Because what I see here, and remember this is just a small snippet of that code, is that there are some patterns here that really stand out to me. The first is this one. You know, you see that? You have an if statement with some kind of complex expression, and after that, there's a lengthy block of comments. To me, as I use this as a heuristic, this is almost always a clear sign that this function is doing way too much. this should most likely be a separate responsibility, something we could have extracted and encapsulated in a function with a well-chosen name. And if we continue to look, we see a bunch of other code smells. We see that there are chunks of deep nested logic, and there are multiple chunks of deep nested logic after each other. This is something I call a bumpy road code smell, right? Like, you know, just like you drive on a bumpy road, that will slow down your driving speed. Bumpy roads like that in code is going to slow down your code comprehension speed. It's going to make it harder to understand that code. It's cognitively challenging. So if we take these code smells, and there are many others there, and we combine it with the fact that this particular class has more than 100 functions of similar complexity, then I think it's fair to say that what we have here is a God class. So how many of you have heard the term God class before? So that's a lot of you. Good, good. So God class is simply a design smell, and we use it to describe classes or modules that compulsively kind of collect responsibilities and also contain a complex implementation like that. Now, God classes have an impact on us as a team. I like to call them the traffic jams of the software world. So what happens with the God class, and the reason it's a problem, is because God classes, since they centralize so much behavior, as a developer, no matter what feature you're intended to work on, at some point you will end up in the God class and you will have to make a change to it. So God classes tend to become very heavily congested. So what can we do about this? Well, what we need to do in this case is that we need to mitigate the technical root cause. We need to design for an increased cohesion in the God class, because there is some pretty good scientific evidence that if we can improve the cohesion of our design, that's going to help us limit the amount of coordination we have to do as a developer team. So I want to show you how we could approach this on a real code base. And now I've been torturing our C++ code base, so let's do the same to a Java code base. It's only fair, isn't it? So this is a golden oldie, Hibernate. So how many people are using Hibernate today? Wow, so cool. So how many of you have looked at the source code? Not as many, but we're going to kind of peek a little bit at it today. So what I did here was that I did an analysis of the Hibernate ORM. And what I find was that one class really stood out, the abstract entity persister. It's a pretty cool name, isn't it? And what I found interesting about that class is that it's pretty big. It contains more than 5,000 lines of code, and it has more than 380 methods. And please, don't let yourself be fooled by the name. Let me assure you, there's nothing abstract at all about it. So I think it's very clear that just looking at those numbers, it's very clear that we seem to have a problem with cohesion here. So what do I do when I come across a class like this? Well, what I try to do is that I start by looking at the method names, and then I try to identify different groups of behavior inside that class. And I kind of try to, you know, put the methods next to each other. And once I've identified like a subgroup of responsibilities, then what I try to do is that I just regroup them. I extract those methods to new classes, and I try to put a descriptive name on them. And the nice thing by doing that is that not only am I going to increase the cohesion of the solution as a whole, you know, making it easier to navigate the code, because if I'm interested in, let's say, the lifecycle behavior, then I have a lifecycle class that I go to, right? It's like a reading magnet. But the big win here is that by increasing the cohesion, we're also going to create natural boundaries for the teams and developers. So if I'm working on the lifecycle and you work on the proxy, there's no need for us to coordinate in the same code anymore. So we're going to come back to cohesion, but now that we have looked at coordination inside the same class, what I want us to do is to look at a potentially more interesting aspect, and that is intermodule coordination, dependencies. So let's talk about dependencies and the cost of change. And one thing I quickly learned about dependencies once I became a software developer is that all dependencies really aren't equal. And I think that as developers, when we talk about dependencies, what we mean most of the time is one class that uses something in another class, right? They are coupled, they depend upon each other. And that's a static dependency. But I think that if we limit ourselves to static dependencies, the ones we can see in code, then two things will happen. First of all, we're going to miss out on the most interesting dependencies because these tend to be logical, not physical. So maybe different pieces of code are intimately connected, but there's a message bus in between, right? So no direct dependency between them. How can we figure that type of thing out? And second, if we limit ourselves to static dependencies, another thing that's going to happen is that our data isn't going to be actionable because any non-trivial program has so many dependencies, and a lot of them are expected to be there. So let's drive towards some additional insights into our dependencies, and let's do that by revisiting cohesion at the package level. So what you see here is an example where we have two different packages, a bunch of classes inside them. And you see that this is a highly cohesive design because we see that there's only well-controlled dependencies between the different packages. And we also see that inside each package, the different elements are connected to each other, and it does look structured and meaningful. So that's good. That kind of signals that the elements inside the package, they kind of belong together. It's cohesive. We can contrast this with what a low cohesion design would look like. So in a low cohesion design, we will typically see that we have a lot of unmanaged dependencies that kind of ripple across our package boundaries, right? And also, even inside the same package, there tends to be very, very tight dependencies. And that type of design is disastrous, not only to us as individual software developers, but becomes really, really problematic once you throw a team on a design like that. And that's what I want us to explore. So how can we, given a particular design, how can we pick out the most interesting dependencies? Well, we can do that, and it's based on a fundamental fact. Code always changes for a reason. We never change code at random. I mean, if we do, then we might have bigger problems than cohesion, right? But code changes for a reason. And software architecture is very much about making these changes easy, be they bug fixes, new capabilities, or non-functional requirements. So what if we can step into the shoes of the developers coming before us and evaluate how the actual modification patterns have propagated through the architecture and compare that against the desired patterns? This is a behavioral code analysis technique called change coupling. So how many of you have heard about change coupling before? So just a few of you, so that's really good, something new, cool. So change coupling cannot be calculated from source code alone. It can only be calculated from the evolution of your code, which means, again, that we tap into the Git history. So what I do here is that I simply look at files that keep being changed as part of the same commit set, no matter what the author is. And I want to show this in an animation because I think it's simpler to understand that way rather than looking at the raw history. So let's pretend here that we have a particular system we're working on. And we see that in the first commit that someone did to that system, they changed the login module and the chess module and then something else together, right? So it's part of the same commit set. In the next commit, we see that we're changing a completely different module. So it's not related to a first. But in the third commit we do, we see that we are back to changing the login module and the chess module together again. That's really strange, isn't it? If this is a pattern that continues, then we know that there has to be some kind of logical relationship between login and chess because they kind of keep co-evolving like that. So that's change coupling. They are coupled in change. And what's interesting with change coupling is that change coupling in itself is neither good nor bad, so it needs to be contextualized. And I want to show you a couple of examples on that, but let's first explore change coupling. So again, what I do here is I visualize it, and now after C++ and Java, let's turn our eyes to a .NET code base. So this is ASP.NET Core that I visualized here, and it's the same type of visualization. But what I can do now is that I can also overlay the change coupling and see how it looks. So the first thing I want to look at is a package called integration tests. So let's see what the change coupling looks like in the integration tests. You see the lines connecting the different tests? What does that mean? Is it good? Is it bad? Well, from a package cohesion perspective, it looks fairly good, I have to say, because, I mean, all dependencies, you see, they're inside the same package, right? So nothing kind of depends on anything outside. So it seems to be a proper boundary. What would worry me, though, is that all these different tests, they seem to be fairly tightly coupled, right? And that can quickly become expensive. You know, I make some change to the application code, and now I'd have to kind of hunt around for failing test cases in the integration, right? So this is something I would probably look into, but I wouldn't be too concerned since it seemed to be well encapsulated. I can contrast this with another type of change coupling that doesn't look to be as cohesive. So this is an end-to-end test called razor page test. And what this means is that when I modify that particular test, then I have predictable modifications in like 1, 2, 3, 4 different packages. I don't know about you, but to me, this looks pretty expensive. What do you think? Yeah. So this is an example of a low cohesion design. Now, as I said, change coupling in itself neither good nor bad. So that means we need to take whatever change coupling we identify and we need to compare it against our expectations. And when you do that, you will typically see that your change coupling dependencies will fall into 3 different categories. And I want to show those 3 categories to you here. So the first one is something I call desired change patterns. And again, all of this is done on real-world code bases. So what we see here is that we have some application code and some test code that evolve together. This is a good thing, isn't it? It's basically showing that our tests are being kept up to date. So this is the type of coupling you want to see. Let's look at a slightly more challenging case. So this is a model view controller architecture. And you see here that when I modify something in the view, maybe I want to add a new field, a new checkbox or whatever, then I have predicted modifications in both the model and the controller as well. Is that good? Is it bad? Let's do a poll. How many think that this is really good? Not so many, like 3 brave souls. How many think that this is bad? Okay, bad side wins. So my take on this is that given the context, again, we need to interpret this from the desired context. A model view controller pattern more or less encourages this, right? So we're following our pattern, which is good. We have some predictability. On the other hand, the problem is that we're following our pattern. This is a pretty expensive way of doing things after all. So we can always question, does this architectural pattern really make sense for the problem we're solving? However, I want us to contrast these 2 findings with the third one. Remember the God classes. This is what a God class looks like in a change coupling perspective. And this is, again, a real code base. This is Telegram for Android. And we see there that there is a God class called chat activity. I don't know much about Telegram, but I think a chat is a pretty important part of it. And we see that it's a massive, massive God class. Basically, no matter what I work on, I have a dependency to the chat activity, right? So this is how we can visualize the impact of God classes. Now, finally, to sum it up, to evaluate change coupling, there are a couple of rules of thumb that I use. First of all, I say that change coupling is problematic when it violates our architectural principles, right? And the reason it's problematic is because whenever we violate our architectural principles, we're introducing a surprise into our architecture. And trust me on this one, a surprise is one of the most expensive things you can ever put into a software architecture. So change coupling helps you avoid these type of surprises and detect them early. Now, a related code smell is, of course, that if we have change coupling dependencies and those dependencies cross team boundaries, then we're not only going to have a tightly coupled system, we're also going to fall into a particular problem that is called shotgun surgery. Has anyone heard about that way of working? Yeah, cool. So shotgun surgery is basically the case where you want to add a simple capability to your program, and now that you find that you have to hunt around in 15 different files and make modifications, right? And these files might be spread out across multiple microservices owned and operated by different teams. So when that happens, the impact goes beyond architecture, right? I promise you that your calendar, if you look at it, it will look like a chessboard, and every single one of these items on that chessboard is going to say sync meeting, coordination meeting, right? So shotgun surgery becomes extremely expensive, and no amount of reorganizations or team patterns are going to help you. What you need in that case is a fundamental retake on your architecture. And my main recommendation, as always, is to align your architecture with the problem domain, like we did with Hibernate before, because that's how we create natural team boundaries. Now, we have already come to the last socio-technical smell that I want to talk about. And this time, I want us to look a little bit more at individual contributors. And the reason I wanted to do this is because getting the people side of code wrong has killed more projects than even Visual Basic. So this is an important topic. And I want to introduce this by sharing a story with you. So those of you who were in my talk yesterday, you know that I do a lot of work in the code quality space and technical depth and all of that. So a couple of years ago, before the pandemic, I think 5 years ago, I did a workshop for a team in Germany. So I went down to Berlin and we sat down for a day to analyze their code and see if we can identify some technical depth and prioritize it and come up with a plan on how to remediate it. And the interesting thing was that that team, they had 2 code bases. So we explored them, we investigated them, and they had some issues, but nothing major, right? So we're pretty confident that we can fix this. However, towards the end of the day, one of the team members told me that, you know what? We actually have a 3rd code base as well. So I said, super interesting, and we still have a bit of time, so should we take a look at that code base? That was not the answer I got. What people did instead, and at first I thought maybe this is just a German thing, because they started to look down in their desk like this. Then they started to look at each other a little bit tentatively. And I thought, what's going on here? And then someone suddenly told me that, no, we don't need to look at that code base. We don't need to look at it. And I think the technical term he used was that that code base is a mess, right? So I said, okay, but now we definitely need to look at it. So we did. And guess what? That 3rd code base, how much worse do you think it was? Objectively, it scored exactly as well as the other 2 code bases in all metrics. It wasn't worse in any sense of the word. And the team were very skeptical about this, very skeptical. So we had to spend like 20 minutes picking up different code samples and comparing and looking at the end of the day, everyone was convinced that, yeah, indeed, Codebase 3 is not worse than the others. So what happened? Why did they have this perception? They had this perception because Codebase 3 had a very different story. Codebase 3 had been developed in a different part of the organization, in a different part of the world, by a team that had since been disbanded. And this team in Germany had simply just inherited that codebase without the proper onboarding. So the reason they thought this was complicated had nothing at all to do with technical depth or code complexity. It was simply a lack of familiarity with the domain and with the code. So a main recommendation to you is to always go to the root cause, because it's so easy to confuse a lack of familiarity with code complexity. And when we do that, we will solve the wrong problem. What this team needed wasn't a major refactoring effort, right? What they would have needed was proper onboarding and proper training and time to learn. So this made me think about this intersection of code quality and the people side of code. And those of you who listened to me yesterday, you might recognize this graph. So this is from one of the code quality studies we did, where we categorize every single piece of code as being either green, healthy code that's easy to work with, high quality, yellow, problematic, red, highly problematic code, lots of technical depth. And on the y-axis, you have the amount of effort to implement a new feature as measured in time, in cycle time. And we see that changes to red code, to problematic code, can be 10 times slower than changes to healthy code. Now, the interesting thing here is when we did this study, we also dove a little bit deeper because we kind of saw that there's a huge variation inside that space of red code. So we start to think, does it matter which developer that makes a change to a particular piece of code? Or are we all interchangeable cogs in a giant machine? I mean, we've all seen this, right? So you have some part of the system that no one understands except person X. And now you need to make a change there, and person X is on vacation for 5 weeks without a cell phone. Anyone ever experienced that? Yeah, we've all seen it, right? So it clearly matters. So we studied this phenomenon. We simply looked at, okay, which developer has written most of the code? How quickly can the main developer make a change compared to someone else on the team who hasn't worked with that code before? And what we found here was pretty dramatic, that for small tasks, there's already a giant hit, right? You're going to need almost 50% more time if you're not familiar with the code. And for larger tasks, like a new feature, you're going to need twice the time. So there is a massive onboarding cost already in unhealthy code. And these findings are particularly far-reaching when we consider another common force on software projects, the truck factor. So you might know the truck factor under other names. It's known as the bus factor, or my personal favorite, the lottery factor. But what they all mean is how many developers can leave your team before your code base becomes unmaintainable. And when these two factors collide, an unhealthy code base with a low truck factor, that's when you create a situation that I call the highway to legacy code. So let's see how quickly we can create legacy code here. I'm going to show you a legacy code making machine. So the first code base I want to demonstrate on is React from Facebook, a UI library that a lot of you are probably using right now. So according to GitHub, React has had more than 1,500 contributors. So what could the truck factor be in React? That is, how many people could leave before we lose 50% of the detailed knowledge of the code? What do you think? 1,500 contributors, 200 people, 100 people? 10, wow, that's a low number. The actual truck factor in React is 2 people. If the wrong 2 people leave, you're going to lose 50% of the detailed knowledge of the code in React. And now you think that, okay, maybe I just pulled that out because it's such an extreme example. So I think it's only fair that we look at the competing framework, Vue.js. What's the truck factor in Vue? Yeah, it's half the one in React. And in fact, in Vue, I'm going to lose 70% of the detailed knowledge if just one person leaves the code base. Which one would you be the most worried about? Both. Both is a good answer. I would actually be slightly more worried about React, despite it having, twice the truck factor. And the reason for that is because if you look at this visualization, you see that there are some dashed borders around certain files, right? That's something that indicates an elevated offboarding risk. So that's an intersection of low truck factor, meaning the code is written mainly by one developer. It also has a lower code health, meaning that it's going to be expensive, remember those onboarding costs, to onboard a new developer. And it's also a hotspot, meaning it's heavily developed. So if I take all these 3 factors, I know I have an elevated offboarding risk. And you see there's a whole cluster of these in React. Whereas in Vue, I really only have one. On the other hand, it's in something called a compiler. I don't know Vue either, but compiler might be important, who knows. So what I want to show you with this is that code quality issues amplify organizational problems. And when it comes to refactoring and technical debt, I highly suggest that we let community smells be a driver for refactoring. So it's not always about paying down the worst technical debt. Instead, we should prioritize improvements to unhealthy code that also has a low truck factor. Because if we do that, we can mitigate a lot of future risks, and we can also remove a lot of key person dependencies. And trust me on this, it's no fun to be a key person, right? You're always going to be pinged. So we have come to the end of this tour. And what I want to show you today is that when we do software design, we also do a lot of social design, and we need to keep both of these sides in check. And a socio-technical fit benefits the people organization. So what we have seen today are examples on how we can not only simplify the onboarding by flattening the technical learning curve, right? So we can get new peers quicker up to speed. We can also reduce key person dependencies by making code cognitively affordable and easy to onboard others. And we have talked about how we can decouple teams via cohesive designs so that we can get more done faster, and in the process minimize defects and improve team morale. And if this sounds all too good to be true, then rest assured that everything is supported by proper research. So I want to leave you with a list of research papers that covers the stuff we have talked about. A lot of the socio-technical smells, I've pulled them out of Your Code is Crime Scene, where I discuss this in much more detail if you want to read up on it. And for the analysis, I want to give credit to CodeScene, which implemented all these analyses and visualizations. So if you want to try this on your own code, please have a look at CodeScene and see what you find. With that said, I'm hanging around for until the afternoon. I'd be more than happy to discuss this during our break, so please just catch me. And thank you very much for listening to me.